Hi, it's a pleasure to host Marc Shapiro. Marc Shapiro is visiting from INRIA. Marc is working on eventual consistency and distributed systems, which is why our research interests coincide. Marc also worked for Microsoft before. He was leading the distributed systems group in Cambridge for 6 years. And I also found out today that he invented proxies a while ago. So from this on, I'll make Marc take over and tell us everything about eventual consistency.
Okay, thank you. So I'm going to tell you about eventual consistency and a subset of eventual consistency, which is strong eventual consistency, which I'll explain in a minute, and CRDTs, which is a particular approach. The whole idea is to have very scalable and very fast replicated objects. So imagine you have some data structure that you want to replicate in the cloud on a large scale. So for instance, you have this graph that's supposed to represent some data of interest, and you want to be able to access it at large scale. So you want to have lots of replicas in different machines spread over the network, possibly in different geographical locations. So, of course, having lots of replicas is great for fault tolerance and it's great for latency, for read latencies. But as soon as you have updates, of course, you have a problem because if you synchronize your updates, then you're slow. And if you don't synchronize your updates, then you have conflicts. So what we're trying to look for is some approach that will allow you to do this, to have replication, but also have very, very high performance for both reads and writes, and will also be simple. Okay, so the conclusion I'll come to at the end is that we have a particular class of objects which are called conflict-free objects. So that's what CRDT stands for, conflict-free replicated data types, which are objects where you can do updates without any synchronization and still have guarantees of eventual consistency. And so I'll show you how sort of a little bit of the theory behind eventual consistency and CRDTs, and I'll also try to address the question whether you can actually use these things in practice. So back to my data structure, I have this graph. Maybe it represents say the structure of the web, and well, since the structure of the web is changing over time, you want to be able to also change the graph. So you have operations to add and remove edges and vertices, and all this has to work very fast because you need to follow the changes of the web, and it also has to scale to very large because the web is so big. So the contributions, the things I'm going to talk about in this talk. So it's, as I said, a model called strong eventual consistency, and this is a sort of a solution to the very well-known CAP problem. I'll explain this in a minute. I'll give you some formal definitions. I'll give you some sufficient conditions. So if you have a data type that fulfills these sufficient conditions, that's enough. You don't need to do anything else. You automatically have all the nice properties. I also prove that these two conditions are actually equivalent to each other. And there are two very different ways of looking at the world. I also show you that this is incomparable to existing consistency criteria. So this is all sort of the theory, and then I'll also talk about the practice. So I'll give you some examples of object types that fulfill these conditions. So I'll start with a little bit of theory consistency. So you probably all know about strong consistency. Okay, this is sort of the ideal that you would like, that every time you do an update, everybody knows about the update immediately, and therefore your programs never get confused because all your threads, all your processes, wherever they are in the internet, have the same view of the world. Okay, so strong consistency means basically that every time there's an update, there's a total order of your updates. Okay, so even if you have concurrent clients trying to do a particular update, they'll be ordered in some order, and everybody's going to see the same order. Okay, so basically there's a counter implemented somewhere in your network, and everybody has to follow the same counter. So everybody knows that the first update here is adding this, purple subgraph, right? And everybody knows that the second update is, I think I deleted something up here, right? And then the third update is going to be something else, right? So I'm adding a new edge, and the fourth update, I deleted some stuff on the left, etc. Okay, but you can see that this is going to put a bottleneck on your system, because basically where you had a big parallel system, now you've made your big parallel system into a big sequential system, right? So maybe this is good for fault tolerance, but it's really bad for performance. The way you implement this bottleneck, this serialization bottleneck, is called consensus. So it's a well-known problem in distributed systems. It's sort of the basic problem in distributed systems. How do you get multiple processes to together decide on a particular single outcome? It's been very well studied, and it's very well known, of course, that this is a serialization. This is a bottleneck. It doesn't scale very well. Consensus doesn't scale very well. There are fault-tolerant versions and sort of peer-to-peer versions of consensus, but they still don't scale very well, and they never can tolerate more than half of your processes being crashed. So consensus allows you to implement this very nice model, okay, which is also called sequential consistency or linearizability, etc. But as I said, it's really bad for performance. So people in the cloud space have been working on something else. And so first of all, this started quite a long time ago with things like Usenet-Use and disconnected work with laptops. How can you do updates that are uncoordinated and still converge towards something? So this is called eventual consistency, and basically the idea is you can update one of these. You can update your different replicas. You can do different updates to different replicas in parallel, and so they'll diverge for a while, but eventually they'll converge. So something like this is going to happen. So one of the replicas is going to add this purple, subgraph. The other replica just deleted this subgraph down here, and then the top replica. And so I'm continuing to delete at the bottom, and now the update that this top replica is going to propagate somehow to the bottom replica, and lo and behold, we discover there's a conflict, right? Because I tried to create an edge to this vertex, and this vertex has been deleted, and therefore this graph doesn't make any sense. Okay, so in eventual consistency, the idea is when you see one of these conflicts, you reconcile. So there's some sort of a global decision about what the outcome is going to be. Okay, obviously, I can't leave the graph like this because it's not a graph. It's not a proper graph. So I have to do something. And there's basically, in this case, there are two things I might do. I might say, well, this, adding this subgraph is incorrect because there's no vertex here. Or I could say, well, the delete was incorrect, right? It doesn't really matter as long as you make one of these decisions. But everybody has to make the same decision, of course, right? So again, this reconciliation requires a consensus in order to do it properly. Okay, the win, what you've gained from the previous version, the strong consistency, is that the consensus, which remains complicated and remains a bottleneck, is now in the background. Okay, so even if your system is, your system is partitioned, for instance, or if more than half of your replicas are crashed, you can still make progress. Okay, because you don't have to do the consensus right away. You can do it later. Okay. So this is what is known as eventual consistency. Now I'll move to No, not yet. So this is what is called eventual consistency. But you can see that this arbitration is still very complicated. Okay? And it's actually a lot more complicated to do eventual consistency in this style than to do strong consistency. Yes?
So I'm saying that consensus now, there's no guarantee of when it is run, it's just sometimes eventually should be run.
Yeah. Yes. So in strong consistency, the consensus is a bottleneck. It's in the critical path of your application. Here you've moved it off the critical path. So performance-wise, it's better, but complexity-wise, it's really very difficult. And getting the reconciliation right can be very complicated. Yeah.
The reconciliation has to be deterministic with these two copies. Can be diverged or?
It doesn't matter because whatever you do, eventually you do consensus. So you can diverge in arbitrary ways, right? And you can sort of converge pairwise. I could reconcile with you, and then you could reconcile with Sebastian, etc. So that could be non-deterministic. But eventually we have to come to consensus of what the real reconciliation is going to be. So anything you do before the consensus is tentative and it is going to be thrown away anyway. Yeah.
Now, but aren't there sort of some arguments, sort of operational transformation, where they will try to reach agreement without communication?
Next one. Okay. Question? Yeah. Okay. Okay, so I'm going to show something which is slightly different, which is a subset of eventual consistency, which I will call strong eventual consistency. And I would argue that what you really want, at least in cloud systems, is this. Okay, so strong eventual consistency starts with the same idea. You can do your updates locally, and you can propagate your updates to each other, right? So here I've done, added the purple subgraph there. I've deleted down there. I've deleted the part of the subgraph down here, and now I'm going to propagate. Okay, and what's going to happen here is I'm going to say, well, okay, this thing is illegal. Fine, just get rid of it. Okay, so I'm not going to try to do any sort of consensus. I'm just going to say I have a deterministic outcome for any conflict. So basically, I'm getting rid of conflicts. Right? There are no conflicts anymore. Everything, any kind of update is allowed, and I just have some recipe to get out of bad situations. Okay. Now, as long as everybody applies the same recipe, that is as long as all these pairs of concurrent updates all have some deterministic outcome, right? We're all going to converge to the same thing, and that's what that's going to be very fast.
Only if the order doesn't matter.
Sorry.
Only if the order doesn't
If the order doesn't matter, right? If it's deterministic, unique and unaffected by what other people are doing on the side, right? Okay, so the nice thing here is that, first of all, I got rid of consensus. I got rid of the complexity of consensus, and I've got rid of the performance problems of consensus, and I've also got rid of the bottleneck, the reliability bottleneck, because consensus only allows up to half of my sites being crashed. This will allow any number of sites being crashed. Okay, so you've probably heard of the cap problem. So the cap problem is this theorem that was uttered by Eric Brewer. It says that in a system you cannot have at the same time consistency, meaning strong consistency in this case, availability, and partition tolerance. So if your system can fail, then you have to choose between either having consistency or availability, right? If you accept, instead of strong consistency, if you accept strong eventual consistency, then you can have all three of these. So now if I look at the sort of formal definition, okay, eventual consistency is defined by these three definitions. So one says that every time eventual delivery says that any operation that is executed at some replica will eventually be executed at all replicas. Okay? Termination says that all executions, all updates will eventually terminate. And convergence says that eventually all the replicas that have received, by this clause, all the updates will eventually reach the same state. Okay, so if your system stops sending updates, everybody will eventually receive the updates so far and eventually will converge to the same value. Okay, but this doesn't preclude diverging, rolling back, reconciling, diverging, rolling back, reconciling, etc. So we don't want that. We want something stronger, and that's going to change the convergence clause. So instead of saying eventually they will reach the same state, I will say that as soon as you've received the same updates, you have reached the same state. Okay? So there will be no rollbacks. Every update is immediately persistent, durable. Okay? So this is going to be my model, and I think this is actually when people talk about eventual consistency. For instance, if you look at what's his name, the guy from Amazon, Werner Vogels, right? He wrote this paper in CACM about eventual consistency. If you read the paper, this is really what he has in mind. Okay. So strong recap, strong eventual consistency says you can do local updates with no synchronization, and therefore you're extremely fast. Okay. Strong eventual consistency gives you consistency, availability, and partition tolerance, right? And it doesn't involve any consensus. So it seems like a good thing. Now, how do you do it? And I'll get to that in a minute. I think I'll skip this slide. I just want to say that if you're interested, we could talk about it later. But at a theoretical level, this is actually a new consistency criterion, which is not comparable to things that have been studied before. So now that I have this idea that I want to do eventual consistency without conflicts, okay, if this is possible, I should be able to have a library of data types that supports these updates without conflicts. And so that's what I'm going to do in what comes up. All right? Yeah?
So what about the order guarantees? If I'm guaranteed the order, then the correctness will not be there, right?
Good question. Excellent.
Okay, so you have to wait a few minutes, and you'll see my object model, and you'll understand what I mean. So when I talk about sufficient conditions, is what are the conditions that guarantee that your objects will converge, whatever the order. Right. Okay, so I'm going to use this, standard diagrams with the time going from left to right, and here I have 3 replicas. Of course, there could be a lot more of some object with some state. So each replica has its own copy, its own view of the current state, right? And then we have some client maybe on the outside who's making calls on methods of this shared replicated object, right? So queries are easy. A query, the client just sends the query to to one of the replicas. It could be any of the replicas, and gets back some state, right? So it's read-only, doesn't have any side effects. And you can talk to, the client could talk to this replica or could talk to the other replica. It doesn't make a difference. The thing is that the system, you can't know in advance which replica is going to get a query, right? So there should be no synchronization in the query path. So queries are easy. Updates are a little bit more complicated. And so there's 2 different ways of describing how updates happen. There's the state-based approach, which says, there's the 2 approaches are state-based and operation-based. So state-based means that I'm specifying the specification of my data type is going to specify what's in the state of a particular replica, and in order to synchronize, I'm going to send the state from one replica to another replica, and somehow they're going to do their thing together based on the state, right? And the operation-based says that whenever you do an update, that's an operation, and you send that operation to all the replicas. Okay, so these are two very different styles of specifying distributed objects, and they've been used in very different settings. Like like state-based in the past has been used for like file systems and for cloud systems, key value stores, and whereas operation-based has been used in the past a lot by people who do the theory and people doing collaborative editing and stuff like that. Now I'll show how they differ. So state-based replication, as I said, again, you have a client who is sending some update method to one of the replicas, but this replica now has to propagate it to all the other replicas. Right? Again, it could do an update on one replica or on another replica, but we're going to assume that these are two different updates. And for instance, we've distinguished them here by saying that they have two. So this update here is going to apply to the local state, S1, and has some parameter, and this update is going to apply to the local state at the second replica, so it's S2 with some other parameter. And the update is going to happen locally at the place where you've sent it to, right? Which I'm going to call the source. That's what this S here means, right? So at the source, you're going to do some computation, and you're going to change the state. You're going to side effect the state, right? So I'm calling the local state the payload. You're modifying the local payload. And then every once in a while, the each replica is going to send a copy of its state to the other replicas. And the other replica, on receiving this copy, is going to apply a merge operation. So the specification of my data type has to specify how I do queries, how I do updates, and how I do merges. Okay?
This is just conceptually. In the implementation, this will be some delta it's sending.
No. No.
S1 could be huge.
But that's the whole idea. Right. Yeah, actually, so we'll come to the other kind in a minute, right? So well, yeah, sure, you could send deltas. Yeah, you could send deltas. But people usually send operations. If they want to send just the delta, they just send the operation. Okay, so and then this replica is now going to talk to the other replica, and that means that eventually and this replica, of course, is going to talk to the other replica. So you have all the replicas every once in a while talking to each other either directly or indirectly, right? So eventually, the first clause, which is that all updates have to eventually be applied everywhere, this is going to happen, right? The second clause says that updates terminate. Well, I assume that's going to be true here, right? And the third clause says that as soon as you've applied an update, it's there and it's not going to change. And you see that this is actually what's happening here, right? So this hopefully this is going to satisfy eventual consistency if it converges. I haven't proven that yet. But anyway, this is the state-based approach. Now, what is a condition? What is a sufficient condition for this to converge? So, if you remember your math courses from a while back, the concept of a semi-lattice might mean something to you. It's actually very simple. A semi-lattice is simply a set with a partial order and an operation that can take any two values and give you an upper bound on those two values. Okay, so if the payload forms a semi-lattice, that is, if there's a partial order of your values, okay, and you can always take an upper bound on two values, right? So if your payload forms a semi-lattice, if your updates always go forward in that semi-lattice, always give you a higher value in your partial order, and if merge computes this upper bound, right? This is a very simple mathematical property, and this ensures that it converges. Okay, I'll give you an example in a minute. But if you just think of, for instance, if your updates are just, if your payload is just an integer, right, and your updates just do some increment to the integer of any value, and your merge takes the max of two values, you can see very easily that this is going to converge. Right? That's your typical semi-lattice.
But if you decrement, that's not the semi-lattice.
So if you decrement, you have to make sure that your decrement still increments in your partial order. So you have to define your partial order so that even decrements go forward. And I'll show you an example in a minute.
So last rider wins is an example of this.
Last rider wins is an example. But last rider wins just takes the max of your timestamp and takes the value that's associated with it. Yeah, definitely. Okay, so this is in the state-based approach. There's a sufficient condition for getting strong eventual consistency, and it's this pretty simple condition. So let's now look at the operation-based approach. So here we have two concurrent updates, right? And now the system is going to in the operation-based approach, you don't send your full state because, as Tom noticed, that can be huge. But instead, you just send the update, right? And you expect all replicas to replay that update, right? So you need something a little bit stronger than in the previous case. In the previous case, each replica just talked to every other replica once in a while, and eventually everybody got everything. Okay? Here you have to make sure that every time you do an update, it is propagated to all the replicas. Okay? So you have some sort of broadcast operation that will send an update and make sure that it is received everywhere. Okay? So I said that you apply the update at the source, but then you also apply it at all the other replicas, which I will call the downstream replicas. Okay? So here, I just had to send the argument to the update, and now everybody of course has the code for the update, so you just need to apply the code at all the sites, right? So of course I just propagated this update. Now I'm going to have to propagate the other update, right? And you can see, well, what happens here is that this guy has applied A followed by B, and this guy has applied B followed by A, right? Now, if you want it to converge, what you want is that your updates are commutative operations, okay? So there you get your sufficient condition in the state-based approach. Sufficient condition for convergence and strong eventual consistency is simply that all your concurrent updates commute. Updates that are not concurrent, right? If I do an update followed by another update, I want those to be replayed in the same order everywhere. But that's pretty easy to do. Okay? So I gave you two different models for replication, and for each one of these models, I gave you a sufficient condition. Now, it turns out that they're actually, I can prove that they're actually equivalent. Okay, so I won't go through that because it's pretty lengthy and not very interesting. But basically, you can take any state-based object and emulate it in an operation-based model, right? And if one converges, the other converges, and vice versa, right? Yeah.
Clearly, you can operate by saying add one, and they commute. But how do you emulate that with state-based? Because max operation is totally different. So how do you do elections by mail in a state-based?
You probably can't do elections.
Because I can operation-based. All the updates needed, I can accumulate 10,000 votes.
But you need to know when you finished. And for that, you can need some sort of synchronization. So yes, that's something you want to know. So this is eventually consistent, but you never know when you've reached consistency, unless you add more synchronization into the system. So I'll skip this one, but if you want, we can go into it. But it's interesting to have these two views, okay? Because they seem to be very different, but in fact they're actually equivalent. And it turns out when you start working with this, you realize that the state-based approach is actually very nice as a reasoning tool. Okay, but of course, if your objects become very big, then it's going to be terribly inefficient. So you know now that you can use the state-based reasoning and then convert to operation-based, and you're still going to win. Okay, the operation-based approach is going to be a lot more efficient, but it's a lot harder to reason about. Now. If you think of CRDTs, so if you think of these data types, as if you think of it in the operation-based approach, right? You have all your updates, concurrent updates are going to be commutative. Now, if I take two of these CRDTs that are independent, obviously they're still going to commute, right? So I can take two of these object types, combine them, and I still have a strongly eventually consistent objects. So I can use this property. So these object types are, I'm going a little bit ahead of myself. I'm calling them CRDTs, but so basically the combination of two CRDTs is a CRDT, but I can also take a CRDT and cut it in half, right? And if the two halves are independent of each other, I still have a CRDT, right? So this is the basis, sort of a theoretical basis for sharding. Okay, if I can take a very large, so for instance, if I take my graph and I can arrange it so that I can subdivide the edges and the vertices into partitions, I can do the updates independently from in each partition. Of course, this only works if the partition is static, right? If you have some sort of hash function that will tell you, okay, this vertex goes in this side and this vertex goes in that side, and everybody applies the same hash function, that'll work. If you want to do something more dynamic, where an element goes from one shard to another, then it's going to be more complicated because you need some synchronization again to make sure that they agree on what they're doing. But static sharding is very easy. Okay, so that's the extent of my theory. And now I'm going to go into some examples, if there are no more questions. So what kind of objects can you use, can you design using these principles? So you actually have a pretty extensive portfolio of designs. We haven't implemented them entirely yet, but basically, of course, you already know about last writer wins, but there's also the multi-value sort of register that's in Amazon, for instance. That's also CRDT. We have different kinds of sets, and I'll spend a little bit of time on one of these variants, which I call the observed remove set. Once you have sets, you can do graphs. Once you have sets, you can do maps, and once you have sets, you can also do graphs. So I'll spend a little bit of time on that. And I'll also spend a couple of minutes on the counter example, because that's the example of a counter, because it's an interesting example. And actually, this whole line of research started with this data type. We were looking for a way to do concurrent editing, right? So you have a sequence of characters, and you want to be able to insert and delete characters concurrently without having any conflicts. So we have an interesting data type here, which is called tree-duck, but I will not go into that unless there are questions.
So
yeah.
If I want just a set and it's not in this list, then what do I do?
You have to tell me what your requirements are.
No, but if I don't satisfy this commutativity condition, then what is my fallback?
Your fallback is to use the usual strong consistency or consensus.
All right.
If you can bend your problem into this small corner, right, which is everything has to commute, all concurrent operations have to commute, then you can use this, right? But it's a small corner of the whole design space. There are lots of things that don't fit into that.
So the commutativity is a sufficient condition set. I mean, do you know of any weaker conditions?
No. I don't think there would be, but I'd be glad to be proven wrong. No, it's a necessary condition as well.
You think so?
Yes.
I don't think so, right?
No.
You can always define converge to be, well, set it to 5, right? And I'm sure you're going to get eventual consistency.
But that's commutative.
I think that's where the confusion comes in. What's exactly the definition of commutative? Because last writer wins is, doesn't feel commutative, right? Because there are different updates and one of them takes precedence. Yet the way it's defined in the data type makes it commutative.
Yeah. As long as...
So it's a lot weaker than it sounds in a way.
Yes.
Okay.
Yes. Okay. Of course, since it's weak, there's a lot of things that you can't do. Right? I mean, if there's the universal, it's been proven that if you have consensus, you can do anything. Right? Now, we don't have consensus, so there are obviously some things that we cannot do, and there are lots of things we cannot do. Yeah.
A way to think about the commutativity requirement is if you had only 2 replicas and you updated both of them at the same time, and they sent their operations to each other. In order to have consistency, they would have to be commutative because they'd both be seeing the exact same things but in the opposite orders.
Right.
So effectively what you've proven is that if your data type allows 2 replicas to be consistent, SEC, then it allows an arbitrary number, which is a nice way to think about it, I think.
Right. But you have to also say that this is true for any initial state as well, and for any argument to your update. Yeah. So let's spend some time on the example. So first of all, let's look at a counter. You think that a counter, for instance, if you take a counter that you can only increment, right? The increment operation is obviously commutative, so it should be very simple. In fact, it's more complicated than you would think. So here I'm looking at the state-based specification. So if you have the problem is that if you have multiple masters, that is multiple replicas that can do an update, right? And if I send this update to Sebastian, who sends it to you, and then I also send it to Same, who sends it to you, you have to be able to tell that those are the same update. Whereas if if Same does an update and sends it to you, that's a different update, right? So in order to do that, you actually need to have a vector of counters, 1 per master, 1 per replica that can do an update. So if each one of us is going to choose an entry in this vector and is only going to update his own entry, right? So my entry is this one. I'm only going to update this one. Same's is this one. He's only going to ever update that one, right? And so the value of this counter, of this increment-only counter, so I can only increment these. So that's going to ensure that I have a partial order. Right? And that all my updates are going to go forward in the partial order, right? And my partial order is not described here, but it's the usual partial order between vectors. That is, A is less than B if all the elements of A are less or equal to B if all the elements of A are less or equal to all the elements of B. So the value is going to be the sum of these because I'm going to do updates here and you're going to do updates here, and therefore the total number is going to be the sum, right? So to increment, I'll just increment my entry. And to merge, so if I send 15 to some A, being my value, and 20 to Sebastian, the truth is going to be 20, right? So I'm going to take the max of each one of these entries in order to do the merge, right? And this is going to do the trick. This is indeed a semi-lattice. My updates always go forward in my semi-lattice, and the merge function of the does take the least upper bound in the semi-lattice. Okay, that's going to work, but that only works for increments. So how can you do decrements? Well, you just take two of these, right? And you take the difference between the two. So to increment, I will increment this guy, and to decrement, I will increment this guy. My entry in this vector, right? And the value is going to be the value of this one minus the value of that one. Okay. So it's more complicated than you would have thought of, right? There are other ways of doing this, but they're even worse.
So if I use the same for positive and negative, so what will change? That's different semantics, but what is
it will not. Well, it'll be a different semantics. It won't do what you want, what you expect, right? Because you're always going to be taking the max. So you'll never be able to decrement, basically. Your decrements will be no ops. Well, here I have a partial order of this. It's if A is less than B, if A dot P is less than B dot P, and A dot N is less than B dot N.
Some of my decrements will get lost. Not all of them.
No, they will all get lost.
I mean, if only the decrement, then no.
They will all get lost because you're always taking the max. So every time you do a decrement, it's going to be forgotten.
That's the first time you work.
First time the positive is the name of it.
So of course you assume that this all starts with zeros in both vectors.
With the local,
sorry?
Your cumulative delta with the local increment in timestamp.
Yeah, it's complicated.
That's about as complicated as this. This seems simpler. You still have to send two values per minute.
So I could also do this with a set, right? I could have a set. Every time I want to increment, I add some new element into the set. And so for the add-only version, right? And to merge, I would just take the union of my sets. That would also work, but that would grow indefinitely, and it's not very nice.
Still, okay, my intuition is not like counter pluses and minuses are commutative. That's like what I'm coming from, right? Like my intuition is that.
Right. So if you think in the operation-based approach, right? All you need to do is to send the increments and the decrements, and that, yes, that's definitely going to work. Okay. Right. But here I'm putting myself on purpose in the state-based approach. Right. Okay, so now I'll move on to something else with how do you do a set, right? So a set is something I've decided that a set is something that has these two operations. An operation to add an element, and an operation to remove an element, right? And the the invariants are whatever the initial state is after I've added E is going to be in my set, right? And whatever the initial state is, when I remove E is not in the set anymore. Okay, seems reasonable, right? Okay, so the sequential semantics are well defined. Now, what happens if you have concurrency? What happens if you have concurrently add E and remove E? What is the outcome going to be? Okay. Now, you could say, well, I want a linearizable system where there's a total order, and the last the system makes some decision and puts one of these last, right? Okay. That will give you exactly the same semantics as the sequential semantics, but it involves a consensus, so you don't want that, right? It's not SEC. Well, it is SEC, but it's too strong for what we want to do, right? So I cross this solution out, but there's still many other solutions. So you could say, well, I will mark this as an error state and just let the user decide eventually. That is a perfectly valid answer, that will give you SEC, right? Or you can say last writer wins. I will put a timestamp on this, and one of these will win, but everybody will make the same one win. Right? Or you could say the add always wins, or you could say the remove always wins, right? And each one of these is a reasonable semantics and really depends on what your application is, right? It turns out that the one that is, besides the linearizable one, the one that gives you the most intuitive semantics is add wins, and it also is what I need for my applications. So I'm going to spend a little time on how do you design this, okay? And I'm going to call this the observed remove set. So the idea, so let's start, I'll give you an example execution to understand how this works. So we'll start with an initial state where all the replicas are empty. And so the first replica is going to add some element A. So in the interface, it's a set, right? So if I add A 10 times, I still have only one A. And if I do a remove, it's gone, right? Even though I did 10 adds. That's the semantics I want, okay? But internally, I have to distinguish these different elements, these different adds, sorry, okay? So I'm going to internally add some unique identifier that is going to distinguish different instances of A. So externally it's all A, but internally I make a difference. Okay? So here I have A subset alpha, which is my unique identifier for this particular instance. And this guy is also going to do an add A, and it's distinguished by a different unique identifier. Now we propagate the state down here, and obviously the merge function is going to be to take the union, right? So here I have, so far I've only received this state, so in my state here now there's only A with the beta unique identifier. And now I receive, the third replica receives this state, and the merge is going to take now in the state. Internally, there's two distinguished instances of A, but of course externally I'll just say there's only A. Right? And now I do a remove. And here we have concurrency between this remove and this add. Right? But you can observe that this guy doing the remove, he can only see this A. Right? He cannot see this A. So it would make no sense to try to remove this one, right? So that's why I've distinguished the two. So now this remove A is going to remove from the set. Actually, it's not going to remove. It's going to mark as being deleted all the elements that it could observe, all the A's, sorry, that it could observe, right? In this case, it's just A alpha. And now I'm going to propagate this deletion mark down here, and I'm going to merge the two states. And now my state here is A has been added here, and a different A has been removed here, right? So A is still in my set. So you see, I have a concurrent remove and add, and the add wins.
So the general pattern between this and the integers is that you're using more memory space to get your sort of intuitive merge. Sort of deferring, here you're deferring like the allocation of some of the A's because you're hanging on to them longer than would be necessary in a strict sequential setting.
So what's common in both cases that I have this semi-lattice and I always have to go forward, right? So in the integer case I had to separate the increments and the decrements, right? And here,
about separating things,
right? And here I have to mark deleted items. I have to keep them as deleted, right?
As long as
tombstones. I'll get to that.
Oh, okay.
Right. Okay. It turns out that you can optimize this and you can actually remove them right away. Okay, but I will not get into that now.
Okay.
Right. So now I want to show that this is going to converge. Okay. So now let's say that this state is going to be propagated, right? And now you're going to take the union between this, and that's what you get. So you have the same state in both cases, right? And, well, this guy so far has not seen the deletion yet. He's only seen the add A beta, right? But eventually he will receive the same stuff, and he will converge to the same state. So there are different designs for sets, right? There's a design which is well known in literature, which goes back to the 80s, which we call the 2p set, which is where every element is unique, and you add it, and you can remove it, but once it's removed, you can never add it again. That's a much simpler specification, much simpler design, but it's much less intuitive because you can never add things back. Here's a design where you can add and remove an element and add it back and remove it, and you get very close to the sequential specification.
Is this equivalent to implementing a set by using a multi-set, and when you remove an element, you will remove as many elements as are in your multi-set?
That doesn't work.
Okay.
That doesn't work. There are people who try to do that. So you associate a counter, basically, right, with your element, and every time you add an element, you increment the counter. Every time you remove an element, you decrement the counter. But then you get into anomalies where your counter can become negative. And then when you add something, it's still not there. Yeah.
Actually, if you use the counter that you showed previously, the eventually consistent counter, for each element, I think you'd have exactly this.
No, it's just as I said, the counter can go negative.
How can it go negative?
Because if I add A, and Same and Sebastian both concurrently remove A, right? I set the counter to 1, and they're going to decrement it by 1 each. It's going to go to -1.
Right. Yeah. Because they're deleting my A, not their own.
So, question: the bottom specification there, if in between, if the let's say the add and the remove happen concurrently, but in between them, the node that does the add communicates with the node that does the remove. Because we're not specifying maybe perhaps when those communications happen, then the result would be that E is not an S, right?
It's not concurrent in that case, yes. So it would be add followed by remove, in which case the thing is empty.
But then you're including that communication in your concurrency specification.
Yes. But that's the definition of concurrency. Concurrency means there's no communication. There's two independent updates.
Seems like in the last line of the specification, you need to add alpha. You say add E. If alpha adds E or alpha removes E, E is in the state of alpha. Because S state is different on every process. So there's different specification for every.
These internal identifiers are internal. They don't come through the interface, right? In the interface, you just have elements, and you can add the same element several times. And
S. This is the public state of this object. In the last line.
No. There's no public state of the object. You can only use the methods, right? So you can look up through the lookup interface. There's no way of distinguishing two E's.
And then you look up like needs to stick to the same kind of copy. So that's what I'm saying. That the E belongs to S. It's like it needs to stick to the same S. So
S is the global state.
But like, how do you define? How do you say that it sticks to the same S specification?
So.
What is S is the question.
It's whatever your state is. So if I have some replicas here, right, and I have add here, right, remove E here, and then eventually these guys communicate with this guy, right. This guy is going to see there's a concurrent add and remove, and then for the E is going to be in the set for any replica.
So by assuming eventual consistency.
Yes. Once you have been able to observe both the add and the remove, then you're in the state where you've seen them both, and therefore you're in this state. Right? Okay. So, by the way, sorry, yeah?
Okay. Now, forgetting garbage collecting the tombstones, or when you can kind of compact the history?
So it turns out that, in fact, in this particular case, you can actually remove the, let's see, so in the operation-based approach is a lot easier to understand. If I create an element, right, and I send it to you, okay. Underlying all this, there's going to be something like vector clocks, which will allow you to compare what things happen before other things, right? So if you receive from me a version that contains A alpha, right, and then later you receive another version that doesn't contain A alpha, and you compare the vector clocks, you can see the second one comes after the first one, you know that A alpha has been deleted, right? So if you have vector clocks, then you don't need to maintain the tombstones. You can throw them away right away. So I think I've been talking for an hour, so do I need to stop or continue? I still have, I'm not sure how many more slides. I have a few more. I can stop at any time. Just, just stop me.
We have the room. It's
okay.
Only depending on if the audience feels.
Yeah? Okay.
I think that's the only
All right. Okay. So as I said, there's some optimizations. You can get rid of tombstones. You can make this more efficient by using the operation-based approach. Snapshots I'm going to talk about in a minute, and sharding I'm also going to, well, I already told you about sharding, so I don't need to talk about it now. And it's interesting to see that this actually solves, if you guys have read the Dynamo paper, there's they have this example of the Amazon shopping cart, and they say, well, it's very weird because we have this shopping cart which is wonderfully available, and basically what they're trying to do is strong eventual consistency, right? But it's strange because when you add a book to your shopping cart and then later remove it, sometimes it sticks, it comes back, okay? And what happens is the problem they have is that they haven't used the right data type. They didn't use something that is properly designed as a set. They use something which we call the multi-value register, where the only operations are assignment. There's no add and remove, and that's why it doesn't work properly. So if you take the time to actually design a set, you can do it properly. So when you scale up, you need to be able to do sharding, so I explained that. But you also need to be able to do consistent snapshots. For instance, if you're looking at different replicas or different shards, you want to be able to make sure that the data that you're looking at is consistent. So it's very easy to extend the OR set specification to get consistent snapshots. I told you that each element has an internal unique identifier. If you just use some clock for this unique identifier, that gives you the capability to do consistent snapshots just by deciding in advance what's the clock value that you're interested in, and you can tell what is in the set and not in the set at a particular clock time. But then you cannot use the optimization to get rid of tombstones. You have to keep them. Okay, so I told you about set. Now, if you can do a set, you should be able to do a graph, right? A graph is just a pair of sets, right? So, you know, a graph is a set of vertices and a set of edges, and where an edge is, you know, some pair of vertices. And the sequential specification of a graph, you know, is very simple. You know, you have so basically it's the sequential specification of sets plus this invariant, right? So it says that you can only add an edge if the two vertices are in the vertex set, and you can only remove a vertex if the if there is no edge if there's no edge that uses that vertex, right? Now, so this adds a new problem. Okay, I already had the problem of concurrent add and removes within each set, which I solved with OR set. Now I have a new problem. What happens if I have concurrent remove vertex with add edge, right? So if I'm trying to remove a vertex, even if I think locally that I'm allowed to do that because there's no edge between it, there might be somebody adding an edge, right? So what can I do? Again, I could try to use, you know, to stick to the sequential specification, but then I have to use linearizability. Or if I want to use, you know, strong eventual consistency, I have to have some well-defined unique outcome, right? And again, there's a whole choice of what that outcome can be. We will use for our purposes, which is you know, modeling the web. It turns out that add wins is the specification we want. So I'll just spend a little bit of time to see, you know, how can we? Well, actually, I've already given away the result, right? The result is that you just have to choose some unique outcome for that. So the way we do this, we implement this as a pair of sets. So there's a set, an OR, observe remove set of vertices, and an observe remove set of edges, right? And basically, what we do is we do not try to enforce the invariant, right? So if you want to add an edge or you want to remove a vertex, fine, just go ahead, right? And we'll check the invariant on lookup, right? So if you try to, you know, create an edge to something that doesn't exist, when you do the lookup, we'll just say there's no edge in there, right? And that's consistent with the semantics of the web, right? Where you can create a URL to something that's not there, and that thing might appear later or it might never appear. Okay, so that's why this is the right semantics for us.
Eventually, that invariant will eventually converge to something. It may be false for a while, but once it becomes true in the presence of no more updates, it won't become false.
You'll never know. You'll never know. It's just when you try to do the lookup, we'll say, no, there's no edge there.
That's what I mean by the lookups. Eventually, if there are no updates, the lookups will be consistent.
Yes, but, yeah. No, but even at any point in time, that's not even eventually. Just now, if you do the lookup now, and you happen to observe that the you know, target, the head vertex has been deleted, you will also, by side effect, observe that the edge has been deleted. So basically, deleting an edge has a side effect on, deleting a vertex has a side effect on the edges.
You said earlier, the previous slide, you said add edge wins. That was just really meant remove wins?
Remove wins, sorry.
Okay. And then, is there a reason to not enforce the invariant for local operations, in the sense that if I go try to add an edge between two vertices that at the moment don't exist on my replica, it might be useful for me to know that and have that fail. And really, you're avoiding enforcing the invariant just for deltas that come in.
So there's two reasons why I'm not enforcing the invariant. One is because I'm trying to stick to the semantics of the web, where you can create a URL to something that doesn't exist. That's fine. And the other reason is for sharding. Okay, because if I shard, I don't want to have to be able to check with a remote shard whether my invariant is true. So this is basically the execution that we saw at the beginning. And okay, so this is what I was going to tell you about sharding. So for sharding, each one of the sets is sharded using the technique I described earlier. And as I just mentioned, using this semantics is good for sharding because I don't have to look up a remote shard when I create an edge or I delete. So yeah.
The shards will have replicas on the edge.
So you might have this vertex in one shard and this vertex in another shard.
You both know about the neutral edge.
No, only this guy does.
Okay. How does the edge exist at all?
When you do lookup, then you'll have to look up this vertex.
So lookup is now a distributed operation.
Yes. So I moved the burden of the work to lookup. But I can do consistent snapshots. Okay, so I will do a consistent snapshot and then do a lookup on the consistent snapshot. Okay, so that's basically what we've done. We've designed all this stuff, and we're only just now implementing it. So this work is being funded by a grant from the French government and also from a grant from Google. So basically, we have 3 years to study all this, the theory and the practice of CRDTs and strong eventual consistency. And what we're thinking of doing is something like this. We're thinking of, so if you look at the semantics, for instance, of a web search, all the stuff that's in there, well, not all the stuff, but a lot of the stuff that's in there is amenable to CRDTs. So basically, if you want to, if you crawl your websites and you create a local copy of your website, basically, it's going to be a map of a URL to some content, right? So that's just a map. If the graph, I showed you how you can do a graph as a CRDT, the list of words in your system is just a map again. So a lot of these things could be implemented as CRDTs. We combine the three things. One is CRDTs, the other is sharding in order to scale, and the other thing is using a data flow approach in order to do your updates incrementally, right? And to just push them down the data flow. So, for instance, if you crawl your websites, you can say compare each page with its previous version, and then you can tell which links have been added and removed, which words have been added and removed, and you just need to push those operations downstream. And you would use those operations to update, for instance, the graph and the words. The advantage of doing this is that you can sort of adjust your quality of service according to what kind of resources you have. So if you have lots of resources, you can push all your updates right away. If you don't care about your quality of service but you want to save on resources, you can throttle the updates. That's just same thing as what I just mentioned. This one is the same one. And if that's true, if what we're saying is true, then this should be able to scale very well. You could have crawlers that are very local to the website that you're looking at, and then you could just push updates to the rest of the world asynchronously. And you could have lots of copies of this. All these things here are CRDTs, and so everything can be asynchronous. But there's some things that have to be, probably have to be centralized. So for instance, computing the page rank is probably going to be a centralized operation that has to work on a consistent snapshot of your data.
What is the composition story? For example, if I take the classic bank account example, model 2 accounts with 2 counters, what are the guarantees? This is the guarantees.
Eventual consistency, which is not what you want for bank account, is it?
For both? For both or both? Or each one individual?
Yeah. Say, you know, remove $100 from this account and add it to that account. Eventually, you will see the fact that the money has been moved, but you might see states where the money is in both accounts or in neither of the accounts.
So wouldn't the account allow a negative state in this case?
Definitely. Yeah. It's very hard to enforce invariance, strong invariance with CRDT because enforcing invariant means that you might be able to check your, say, precondition locally, right? But then you have no guarantee that your precondition is going to be true at another replica. So, and for the same reason, transactions are hard. Which is why we need to have consistent snapshots instead, as a sort of alternative to transactions.
Is there a paper you pointed us to that sort of sums up the framework?
Yeah, there's a couple of papers in our page.
Okay. Which one in particular?
Well, we can look at my webpage.
Oh, okay. Okay, great.
So anyway, this is supposed to scale to the whole world.
Can I go back and say again? So how do you do the consistent snapshots?
So basically, in the case of the interesting case is the set or the graph, etc. So if you remember, each element in the set has a unique identifier. Okay, you can use a timestamp as that unique identifier, right? And then you can tell at any time, and if you retain tombstones, right, you can tell at any point. You can choose a point in time and say, well, this element was in the set at that point in time, or wasn't.
It's not globally. The timestamp is assigned declines. Because clocks are not synchronized.
Exactly. When you do a consistent snapshot, you need to take a version vector, which is basically a collection of local timestamps. So for each one of these local timestamps, you can tell whether an element is in the set or not.
So you use vector clocks to order numbers.
When you need to keep, you know, if one client kept adding and moving and adding and moving and adding and moving, you actually have to keep significant history
Yes.
in order to be able to construct it at any point.
Yes.
It's not even just one timestamp element.
But that's because you want to be able to do consistent snapshots. If you're only interested in the current state, then you can throw a lot of that stuff away. Okay, so I'm done. Thanks for all the questions. Oh, you want to look at my webpage?
I found it.
Okay.
I found one. It's the topic paper.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.